So section 6 is on the multiplication law of probability, and I'm gonna introduce to you an idea called conditional probability, and really breaks down to these are the and kind of problems or the intersection problems. And so we're going to start off with a simple example here. So suppose a bag contains 6 balls, 3 of them are white, 3 of them are red, and we're going to choose 2 of them. Okay, we're going to go reach into that bag, pull one out, reach into that bag again, pull the second one out. And say our focus is we'd love to choose 2 red balls in a row. I don't know, maybe it's a game, and if you're able to do that, you win a prize or something. Okay. So A is going to be the event that the first ball you choose is red. What's the probability of A going to be? 3 out of 6, right? Because we're gonna assume it's every ball has an equal chance of being selected by you, and you get it, right? And then B is the event that the second ball chosen is red. And so what's the probability of that going to be? Well, how many balls are left? You've picked one out. Are you putting it back in? No replacement. We're not putting it back in. And so there's 5 left. And so what's our probability going to be? 2. Well, are you sure it's 2 out of 5? Well, it depends. It depends on what happened. Like if your first pick was red, then there's only 2 red balls left, and it's 2 out of 5. But what if your first pick was white? Then it's 3 out of 5. And so it depends on your on what happens on that first pick. So it's conditional probability, right? You kind of see where that's coming from, right? It depends on what's happening. So we start to introduce notation here and say, well, we can't answer the question on what's the probability of B because we don't know what happened with that first pick. And so we have to let the person know what happened. So I want the probability of B, but then I need to give you some extra information. So I'm going to tell you that A happened. So it's a little new notation here. So this reads, what's the probability of B given, so this little straight line here is given that A already occurred. So I'm telling you the first ball was red. Now you can answer the question and say, okay, now I know that probability. So what is it? 2 out of 5. Okay. If I said this, well, what's the probability of choosing a B occurring? So the probability that I get a red ball, given that A didn't occur, so I didn't get a red ball in my first pick. Red of 5. And that's down here. I'm just summarizing this. It's all written here, right? But that's the idea. There's some new notation. Conditional probability is what we're looking at. And so what happens is we have this. We end up shrinking down our denominator here when we talk about conditional probability. Let me give you a Venn diagram example. So new events here, and I'm going to put some numbers in here. So say there's 5 outside of A and B. There's 5 in the intersection. There's 10 right here. There's 15 right here. And if I ask you, hey, I don't know what these are, but I'm going to select one of these items, okay? And so what's the probability I select something from A? Assuming equally likely events, or everything's equally likely. What would you say what's the total of everything here? What's 5 plus 10 plus 5 plus 15? 35, yeah, not 40. You got 40? 35. So what's the probability of A? So how many things are in A? 15 out of 35. And don't worry about reducing yet, okay? Now, what if I change it? What if I say, well, what's the probability of A? And I'm giving you some extra information here, given B. So the way you read this is, I still want the probability I pick something from A, but now I'm telling you it came from B. I'm telling you that this item is in B. So now what's the probability that it's in A? So your denominator changes. So I'm not looking out of all 35 because I'm telling you it's out of B. So now you have to add it. Well, how many items are in B? There's 20 items in B. Now, out of those 20 items, how many are also in A? 5. And so what you see happening here is the 5 is the intersection, right? It's the number of items in A intersect B. And then 20 is the number of items in B. Okay? And what if I did this? Probability of B given A. What's my denominator now? Now it's out of A. There's 15 items in A. And how many of those items are also in B? 5. Okay? And so you see this conditional probability. Well, first we look at this. Okay? So the probability of B given A in general is the number of outcomes in the intersection divided by the number of outcomes in A. And that's what you guys were doing. And you can easily turn that into this next piece here. Probability of B given A is the probability of A and B divided by the probability of A. Because what happens, let's go back over here. What's the probability of B in this picture? 20 out of 35. Okay. So notice the probability of A and the probability of B have the same denominator, right? And so here's what can happen. So we got the probability of A over A given B as 5 out of 20. Well, I'm going to divide top and bottom by 35, and I get 5 out of 35 and 20 out of 35. Is that still equal to 5 out of 20? Yeah. But by doing that, I now change this to the probability of A and B. Because if I asked you what the probability of A and B is, you'd say 5 out of 35 over the probability of B. Okay, and so that's what's happening in general with this formula here. That's where it's coming from. And equivalently, we could split this up to this by getting rid of our fraction by multiplying both sides by the probability of A. And we get this formula. And this right here tells us how to find the probability of A and B. Okay. So the probability of A and B is equal to the probability of B given A times the probability of A. Sometimes I write it this way, probability of A. Usually I write it this way, probability of A times the probability of B given that A occurred. It could also be, you can do something similar if I do the probability of A given B. That would be what over what? The probability of A and B over the probability of what? B. And if I multiply that together and solve for the probability of A and B again, I end up with this other one. This could also equal the probability of B times the probability of A given B. So these are equivalent values. Individually, they're not equivalent, but when the products will be equivalent. Okay. So we'll start to pull that apart. But before we do, we're going to back up a little bit and talk about cards because we're going to get into a bunch of problems about cards. And I just need to make sure we're okay with understanding cards, right? And so if you're newer to cards and you forget some stuff, I've listed some facts here. that you're going to want to refer to. All right, and if you just get together maybe for an extra homework assignment, go and play some cards to get familiar with this, right? So you have 52 cards with no jokers, right? And those 52 cards are split up into 4 suits. You got your hearts, diamonds, clubs, and spades. So each one consists of a fourth of that deck. There are 13 cards in each of those. That's what the next point's saying. And the 13 cards are listed here: ace, 2 through 10, your jack, your queen, and your king. So each suit has that. Okay. Half of the deck is red. Half of the deck is black. So your red cards would be your hearts and your diamonds. Your black cards would be your clubs and your spades. And then if we talk about face cards, we're only talking about the jacks, queens, and kings. We're not talking about the ace. There's no face on the ace card. Okay. All right. So as a warm-up here, I want you to try these, but I'm going to modify them a little bit for you. Okay. Just integrate some new notation here. So here you're only drawing one card. And let's change D to the probability of getting a jack given a club, just to work on some of this new notation, so not this one. And let's change, we'll just change that one. Okay, so work A through I, or A through L, that's an L. And you could work together, you could check your answers. I'll give you a couple minutes to try it out, okay? Okay, so I want the answer in fraction form, and I want, before it's good to reduce your fractions, but I want the original, because the original fraction tells us a little more where you started, right? And then we can reduce it after that. But give me the original first. So probability of choosing a king. Remember, we're only drawing one card here. So Charlie, what did you put for that one? Good. So there's 4 kings out of the deck of 52, and that reduces to 1 out of 13. And then B, what's the probability that we pick a heart? Madison, what'd you pick? There's 13 hearts out of the 52 cards, and that's 1/4 of your deck. Okay. Probability of choosing a black card. Okay, would you choose? 8/52, you said? How'd you get 8? Yes. Okay, so let me ask you this. So there's 52 cards, right? And they're split up between four types, right? And so in those 4 types, how many hearts are there? Actually, look at the second bullet right here. Each suit has how many cards? 13. So there's 13 hearts. There's 13 diamonds, 13 clubs, and 13 spades. You go with that? Okay. So, and then some of those are black cards, some of those are red cards. And it says, if you look at the third bullet point, the red cards are your hearts and diamonds, the black cards are your clubs and your spades. So these right here, the clubs and the spades, make up your black cards. So how many black cards are there? 26. There you go. So 26 out of the 52, which is half of our deck. D, a little more challenging question. Just practicing this new notation. It's called a conditional probability. What's the probability we get a jack given a club? Before we give it, let's give you a hint. Whenever you have these conditional probabilities, it's no longer out of the 52, no longer out of the total. It's going to be out of the clubs. that's our new denominator. Okay. So Logan, did you try this one? Yeah. So how many clubs are there? 13. And out of those 13, how many of those are jacks? There you go. Now, if you were to answer the question, what's the probability of getting a jack? We'd still get the same answer, huh, in this problem. And so, which tells us that those two events are not conditional. They're actually independent of each other in this case. And so it worked out okay. If that happens. So anyhow, that's our conditional probability on that one. Probability of getting a red queen. Timothy, what'd you get? Good. Because you got the queen of diamonds and the queen of hearts. Probability of getting an even number spade. Z? You got what? Out of. Okay. So good. Is that the first fraction you started with? Yeah. And how'd you get the 5? So 2, 4, 6, 8, 10 out of 13. And why'd you choose out of 13? Oh, okay. So even numbered spades. I see. So but it's not saying even numbers out of the spades. So if it said, if you had the slash there, then you'd put it out of 13. But what you want to do is if you were looking at all 52 cards, how many of them would be both? So this is like an and problem. It's got to be even and the and is implied. It's got to be even and it's got to be a spade. So you counted the 5 correctly, but you want to make your denominator 52 instead of 13. Okay. But if we had the slash there, then it would be out of 13. So that's the difference there. Probability red or black, part G. Haley, would you think? Where'd you put? 52 out of 52, all of them. So the probability is 1. It's going to happen. Probability of jack or diamond. Liam? How'd you count the 16? You got 13 diamonds plus 3 jacks that are not diamonds, huh? So 3 jacks that are not diamonds. Because the one of the jacks is stuck in that 13. Does that make sense? So the event of it being a jack and the event of it being a diamond, those are not what? Mutually exclusive. You got it. Okay. There is an intersection. You can have one card being both, right? The probability of getting an 8 or a 10, Sierra? Good. Because there's 4 8s and there's 4 10s. So that reduces to 2 out of 13. Probability of getting a face card or a red card, Taya? And how'd you count that? We got 26 red plus, what'd you say about? No, but you're right. There's half of them are red. Now, are some of those red cards face cards, Taya? Yes. So we don't want to count those again, right? So we just want to now count the black face cards. So how many black face cards are there? And how do you get the 9? Well, how many face cards? What's a face card? Okay, so you got 3 face cards for each suit, right? So how many black face cards are there? Which ones are your black suits? Black cards are clubs and spades. So you got 3 face cards in your clubs, and you got 3 in your spades. So how many face cards? There you go. So you got 26 red cards, and you got 6 black face cards. And so when you add those together, we get our 35. Good. That's what I meant. 32. And we can reduce that to what, 8 out of 13? Okay. King or a spade. Probability of getting a king or a spade. Wyatt. How'd you count that? So you use the method we did in H, right? Okay. It's like H a lot. And probability of getting an ace and a king. Let's go with the other Wyatt. 0. Explain your answer. Can't have one card being both an ace and a king. Good job. So look out for the word and, right? Okay. All right. Let's do a couple. So these card types of problems are going to go all the way for us until number 9. Okay. And let's take a look at number 3. So now instead of having one card, we're going to have 2 cards. Okay? One deck. One deck. No jokers, so you're pulling 2 cards. Okay. And we want the probability that they're both clubs. Okay? And so we want the probability that let's see, we're shuffling the cards and putting them down. And so we want the probability that the top card is a spade, right? Or no, is a club. Okay. Did I use the word or and or given? Because it says we want them both to be clubs. And is the key word here. We want the second card to be a club as well. Okay? So that's our problem. And so we need to figure out this probability. What do you guys think? What's that? Okay, so we're trying to reach for a formula, right? And the OR formulas we have, and we have an AND formula. It's right in the beginning of this notes here, right here. The probability of A and B is the probability of A times the probability of B given A. Or you could go the other way if you want the probability of B times the probability of A given B. Okay, we're going to have to really, so it's multiplication and conditional probability. So we're going to have to rely on that. So here we go. So this is the probability. Let's call this A here. And let's call this B, so I don't have to keep writing that out. So this is the probability of A times the probability of B given A. So we're breaking up into smaller probabilities that we can find to make it an easier problem for us. Okay. So what's the probability of A? 13 out of 52. Because there are 13 clubs out of the 52 cards. What's the probability of B? No, sorry, what's the probability of B given A? I said it wrong. Okay, I heard a couple answers. What'd you say? Not sure. What'd you say? Explain your answer. Why 12 out of 51? That makes sense to you guys? Good. So he's finding a conditional probability there. You've already picked one card, so it's not out of 52 anymore. There's 51. And you've already picked a club, and so there's only 12 clubs left. And so now we can reduce this, and so, let's see if we can finish this without a calculator. So 13 out of 52 is 1/4. And we can divide by 4. So we end up with 3 out of 51. Their answer. Okay. So that's the probability that the top two cards are both clubs. Let's try one more. You pick. 7. I heard 7. Okay. George randomly draws a card from a standard deck of 52 cards. Then Summer also randomly draws a card. George did not replace his card. What is the best approximation to the probability that Summer's card is the same suit as George's? Okay. So George picked a card, and we want Summer's card to match George's. So don't worry about percent yet. Let's get a fraction. Fractions are going to be more natural in this problem. We don't know what George drew. Okay, but we do know something about suits in the card. That it's okay. So here's George's card. Here's George's card. Okay, there's George's card. It's face down. We have no idea what's under it. Okay, but how many cards are left in the deck? 51. So you know her problems out of 51, right? And how many cards in those 51 match George's suit? And so that's the probability. Okay. So we're not done yet, though. No calculator. We got to match it with the percent. So if I double this, this is going to be 24 over 102, which is close to 24%. How does that compare with 24 out of 100? Is it bigger or smaller? Which one's bigger? Okay, so it's going to be less than 24%, but it's going to be really close because this is an approximation. Yikes! So is it closer to 24 or 23? And you could try it out with if you get closer to 24%. So homework is to finish all through 12. You're going to have to do a little bit of reading when you get to 10, 11, and 12. Okay.